Hello students, now we will do a correction in Newton's formula for speed of sound in a gas, which is called Laplace correction. After around 100 years of Newton's formula given by Newton, Laplace corrected it or gave a correction. Okay, so we are going to do this. This video is brought to you by Site India e-learning. To join online classes from anywhere and offline classes only Lucknow, please click the link to see contact informations. Thank you. Come, we are going to derive a new formula, that is a corrected formula of speed of sound in gases. In a gaseous medium, in a gas, speed of sound is given by V equal to B upon rho. This is basic formula, original formula. In Newton's opinion, when sound travels in a medium, gaseous medium, temperature of gaseous medium does not change. But Laplace said that when sound travels in a medium, its temperature changes. At the points of compressions, when gas or say longitudinal wave moves in a medium, gaseous medium, compressions and rarefactions are formed. Compressions are the points where particles of the medium are nearer to each other. Rarefactions are the points where particles of the medium are away from each other. Okay. Laplace told us that at the points of compressions, heat is produced. So temperature at these points increases, and at the points of rarefactions, heat is absorbed, say lost. That's why temperature at these points decreases. But this happens so fast that process becomes adiabatic. Okay. So according to Laplace, when sound travels in a medium, when sound travels in a gas, process is adiabatic. Process is adiabatic. Okay. So, in place of bulk modulus B, adiabatic bulk modulus should be taken. So, in place of B, adiabatic bulk modulus Bs should be taken. Okay. Therefore, formula becomes V equal to root Bs upon rho. I think it's clear. Laplace told that when sound travels in gaseous medium, temperature changes. But it happens so fast that process becomes adiabatic, that is, there is no exchange of heat between the process and its surroundings. Now, for adiabatic conditions, Poisson's law is used, using Poisson's law for adiabatic conditions, which is PV की power gamma, PV raised to power gamma equal to constant. We will differentiate it. See, differentiating with respect to volume. On differentiating with respect to volume, the both terms p and v raised to power gamma are differentiable. Then how to do differentiation? See, first term p into differentiation of second term, that is v raised to power gamma, plus second term, that is v raised to power gamma, differentiation of first term p equal to differentiation of constant, which is on the right side. If two terms, both terms are differentiable, then first term into differentiation of second, first term into differentiation of second, plus second term into differentiation of first equal to differentiation of right hand side. Okay, note it, how to do differentiation. Now apply the formula. P gamma v raised to power gamma minus 1. Its differentiation of v raised to power gamma is gamma v raised to power gamma minus 1. That is differentiation d upon dx x raised to power n equal to nx raised to power n minus 1. We have applied this formula, plus v raised to power gamma, differentiation of p will remain dp upon dv equal to differentiation of constant is 0. Okay, note the formula here, power into power minus 1, that is gamma v raised to power gamma minus 1 will be the differentiation of v raised to power gamma. Okay, now or we will find here p gamma, or say gamma p. Take this term on the right side, gamma p v raised to power gamma minus 1 equal to minus v raised to power gamma dp upon dv, or gamma p equal to minus v raised to power gamma upon v raised to power gamma minus 1 dp upon dv. Apply indices here, or gamma p equal to minus v raised to power gamma upon v raised to power gamma upon v, and this v will come in the numerator, that is v. We can write, listen, v raised to power gamma minus 1 equal to v raised to power gamma upon v, and this v will come in numerator. I have done this, into dp upon dv. Okay, v raised to power gamma cancelled out, or gamma p equal to minus v dp upon dv. Clearly, this is the formula for bulk modulus, and we have taken adiabatic conditions. That's why this is adiabatic bulk modulus, or say BS. Now put this value of BS, which is equal to gamma p, in equation 1. Using 1, v comes out root, I am putting value of Bs as gamma p in equation 1. So it will become gamma p upon rho. This is the corrected formula for speed of sound in a gas, which is given by Laplace. Okay, so this way, this is important derivation from exam point of view. You should know or learn it. Have a nice day. Thank you.